Rahul here again from MySlate, and here we will continue our discussion on derivatives. Whenever you have a modulus term in the expression of a function, first you should try to get rid of the modulus expressions, the modulus symbols, right? Try to get the function in the expressions which are like polynomials or trigonometric or familiar functions that you can differentiate easily. You already know that they are differentiable and in their domains, and you know the formula for them. So that's what we'll do here. Okay. So how do we get rid of this modulus functions? First, you try to calculate the value where they take a they become 0. Okay. When does x minus 1 become 0? At x equal to 1, right? And therefore, we know that for x less than 1, this term x minus 1 is negative, right? So the modulus of that would be minus of x minus 1, right? And how about this one, x plus 1? When does that become 0? At x equal to minus 1. So for values of x less than minus 1, this is x plus 1 is negative. So modulus of that would be minus of x plus 1. And for values of x greater than minus 1, x plus 1 is positive. So modulus of that would be plus of x plus 1. So that's how we get rid of the modulus symbol. And we'll also simultaneously draw that on this x axis. Okay, we'll make these 3 marker points 0, 1 and minus 1. Okay, and we have these 3 intervals. Okay, one interval is x less than equal to minus 1. This is the first interval, and we know that is one break point here, right? And the second interval is minus 1 to 1, and then we get the second break point here plus 1, where this one becomes 0. And the third interval is x greater than plus 1, and we get rid of the modulus symbol for these 3 intervals. So let's try to understand the first one here. So for this first interval, x less than minus 1, we have seen that x minus 1 is negative. So when we take the mod of that, we write it as minus of x minus 1 to make it positive. And x plus 1 is also negative, so we write that as minus of x plus 1 to make it positive, right? And likewise for these other intervals. Just to understand this second one here, when x is between minus 1 and plus 1, x minus 1 is negative. So when we take the mod of that, we write minus of x minus 1, whereas x plus 1 is positive in this interval, right? Because we are talking of x, values of x greater than equal to minus 1. Right. So x plus 1 is positive already. So when we remove the modulus, we keep it positive, plus of x plus 1. And therefore, finally, we get these neat expressions for these 3 intervals. And let's try to draw a diagram of this, the curve of this. We will draw a y-axis, and then we will try to look at what happens at x equal to minus 1. As x approaches the value minus 1, we will take 2 points here on the y-axis, 1 and 2, let us say. And what happens at x equal to minus? As x approaches minus 1, you see that this value approaches 2, right? And for values of x less than minus 1, it is a straight line with a slope of minus 2. So the curve would look something like this. Something like this. The slope of minus 2. And we are talking of an interval less than minus 1, not equal to minus 1. So we draw a hole here, right? It just approaches this number of 2. What happens in this interval, minus 1 to 1? Well, at x equal to minus 1, this takes a value of 2. In fact, it is 2 throughout. So it's a straight line. So we are talking of minus 1 to 1. So we have a straight line like this, and here we draw a hole again. Why? Because this interval includes minus 1, but it does not include plus 1, right? So it stops just short of plus 1. And what happens in this third interval, x greater than equal to 1? Well, at x equal to 1, it becomes 2, and thereon it is a straight line which takes a slope of plus 2. So we write that here. We try to draw that here as a straight line, and this one is defined at x equal to 1. Okay, so now we have a function which is defined at all the points, but as we can see visually, that it is differentiable everywhere except probably for these 2 points, x equal to minus 1 and plus 1. Why do we say that? Because as we approach minus 1 from the left hand side, we get a slope of minus 2. That's what we have here, right? Whereas if we approach minus 1 from the right hand side, we get a horizontal flat slope of the tangent to this green curve, which is the slope of 0, which is a differential of this constant 2. So we have two different values of f prime x. So what we say is that f prime x does not exist at x equal to minus 1. And the same thing happens here. If we approach plus 1, x equal to plus 1 from the left hand side, the slope on this curve is 0. And if we approach x equal to plus 1 from the right hand side, the slope of the tangent on this green curve is plus 2. And therefore, this is not differentiable at those 2 points. Even though it is continuous at all the points. Okay, with that we end the discussion on continuity and differentiability, and you see that, let me just remove this diagram here so that you can see the mathematical treatment of what we have just discussed in this example. I am not going to repeat it again, but just have a look at this so that you can follow in the light of what we have discussed. At these 2 points, x equal to minus 1, we have estimated the limit of f prime x as we approach minus 1 from the left hand side and from the right hand side, and we see that the two limits are different, so it is not differentiable. And the same thing is what we observe at x equal to 1. The two limits of f prime x are not the same. So what we see here is that even if we don't draw the diagram of this function, we can still calculate, find out whether it is differentiable or not. Even though drawing diagram makes it simpler to visualize, so it's always advisable to do. Okay, so what have we learned in this session? We already learned in the previous sessions about continuity. We looked at the definition of derivatives, and in this session we looked at several examples to understand derivative much more clearly. We have derived certain formulae for certain kind of functions. We have got a visual feel of how to appreciate the derivative on a graph, and we have looked at this notion of differentiability, how to check whether a function is differentiable or not at a particular point. Okay, so I hope you enjoyed this session, and you would practice enough problems to master these concepts. A lot of practice is required. Please note that the concepts of continuity and differentiability form the basis of this vast field called calculus, which has applications in many fields in the real world, in engineering, in sciences, in economics, and so on. And therefore, it's a very useful subject to learn, not just for your studies, but even for your future profession. Okay, so with that, let me say goodbye, and I'll see you in the next session. Okay, bye-bye.